The Cosmic Microwave Background, A Window into Primordial Energy. Title: The Cosmic Microwave Background, A Window into Primordial Energy. Introduction. The study of the universe's origin and development has always been a fascinating subject for humanity. Exploring the cosmic microwave background, CMB, radiation has granted us a window into the early moments of our universe. This relic radiation from the Big Bang offers valuable insights into the primordial energy that shaped our cosmos. In this article, we will delve into the remarkable discovery of the CMB, its significance, and the wealth of knowledge it has provided us with. Discovery of the CMB. The cosmic microwave background was accidentally discovered in 1965 by Arno Penzias and Robert Wilson, two scientists at Bell Laboratories. Initially, they were puzzled by a persistent background noise interfering with their work. Eventually, they realized that this noise was not due to any equipment malfunction but actually originated from all directions in the sky. Simultaneously, another group led by physicist Robert Dicke at Princeton University was constructing a sensitive antenna to search for radiation left over from the Big Bang. It didn't take long before both teams realized that they had stumbled upon something extraordinary. Understanding the CMB. The cosmic microwave background consists of faint microwave radiation permeating the entire universe. This radiation is believed to have been released about 380,000 years after the Big Bang. Before that epoch, the universe was a hot, dense plasma of particles and radiation that rendered it opaque. However, as the universe expanded and cooled down, protons and electrons combined to form neutral atoms, which allowed photons to travel freely. This event, known as recombination, produced the first light we now perceive as the CMB. Significance of the CMB. The discovery of the CMB was a turning point in our understanding of the universe. It provides evidence for the Big Bang theory, which states that the universe originated from a hot, dense state and has been expanding ever since. The CMB represents the earliest light we can observe, long predating the formation of galaxies, stars, and planets. The CMB radiation is remarkably uniform, with a nearly identical temperature of about 2,7 Kelvin in all directions. This uniformity led to the formation of small fluctuations, which ultimately seeded the large-scale structures we observe today, such as galaxies and galaxy clusters. Studying these fluctuations in the CMB and their statistical properties provides valuable information about the composition and evolution of the universe. Microwave background cosmology. The field of microwave background cosmology makes use of the CMB's unique properties to explore various cosmological parameters. By analyzing the slight temperature variations across the sky, scientists can measure the density of matter, and dark energy in the universe. These measurements have revolutionized our understanding of the universe and have led to the development of the current standard model of cosmology. In addition to revealing the composition of the universe, the CMB also offers insights into the geometry of space. The shape of the universe can be determined by studying the patterns of temperature fluctuations in the CMB. By examining the distribution of hot and cold spots, scientists have been able to deduce that the universe is flat on large scales, supporting the concept of cosmic inflation. Beyond primordial energy. The CMB not only provides information about the primordial energy released during the recombination epoch but also unlocks the mysteries of dark matter and dark energy. As the CMB photons travel through the expanding universe, they interact with matter and gravitational fields, leaving imprints that can be detected and analyzed. Future prospects. With advancements in technology and innovative experiments, scientists continue to explore the CMB further. These observations help refine our understanding of the universe's history and evolution, pushing the boundaries of cosmology to new frontiers. The study of the cosmic microwave background, CMB, radiation has provided us with valuable insights into the early moments of our universe. This relic radiation from the Big Bang offers a window into the primordial energy that shaped our cosmos. In 1965, scientists Arno Penzias and Robert Wilson accidentally discovered the CMB while working at Bell Laboratories. They realized that a persistent background noise was actually radiation originating from all directions in the sky. Concurrently, physicist Robert Dicke and his team at Princeton University were constructing an antenna to search for radiation left over from the Big Bang, and they made a similar discovery. The CMB consists of faint microwave radiation that permeates the entire universe. It was released approximately 380,000 years after the Big Bang. Before that, the universe was a hot and dense plasma, rendering it opaque. However, as the universe expanded and cooled, protons and electrons combined into neutral atoms, allowing photons to travel freely. This event, known as recombination, produced the first light we perceive as the CMB. The discovery of the CMB was a pivotal moment in our understanding of the universe. It provided evidence for the Big Bang theory and represents the earliest light we can observe. Analyzing these fluctuations and their statistical properties provides information on the composition and evolution of the universe. Microwave background cosmology utilizes the CMB's unique properties to explore various cosmological parameters. By studying the temperature variations across the sky, scientists can measure the density of matter, and dark energy in the universe, revolutionizing our understanding of cosmology. Additionally, the CMB offers insights into the geometry of space. By examining temperature fluctuations, scientists have deduced that the universe is flat on large scales, supporting the concept of cosmic inflation. The CMB not only reveals information about primordial energy but also helps unravel the mysteries of dark matter and dark energy. As CMB photons interact with matter and gravitational fields while traveling through the expanding universe, they leave imprints that can be detected and analyzed. These imprints provide insights into large-scale structure formation, galaxy clustering, and the behavior of dark matter and dark energy. Advancements in technology and innovative experiments continue to push our understanding of the CMB.